We're going to be looking at example 1, parts A and B in your section 4.2 notes. In example 1, we wanted to see if Rolle's theorem applies. I've already written the conditions that I need to check. I need to check that my function is continuous on the closed interval, differentiable on the open interval, and that the endpoints are equal in value. If I have those three conditions satisfied, then Rolle's theorem says that there is a point or a value x in the open interval AB where the derivative at that value is equal to 0. Okay, so I'm going to go through my checklist first with this function. The sine function is a continuous function. It doesn't even matter what interval we're dealing with here. So I know that f is continuous on this interval. Okay. All right, I definitely know that I can take the derivative here using the chain rule. So the outside derivative would be cosine, and then my inside derivative would be 2. So I know that f is differentiable, okay, on the open interval. Okay, so the last thing I need to do is to check that the endpoints are equal. So I will plug in, this would be my A value, plug in 0. Okay, so I have the sine of 2 times 0, okay, which basically just means the sine of 0. Okay, so the sine of 0 is 0. So now I'm going to check the pi over 2, the other endpoint. Okay, so I have the sine, I'm going to have 2 times pi over 2. Okay, and I get the sine of pi. Well, that one is also 0, so I do have that the endpoints are equal in value. So I have all three conditions of Rolle's theorem satisfied. So now I can apply it, okay? So I need to find the derivative first. So the derivative is going to be, like I was saying here, the outside function is the sine, and inside is 2x. So the derivative of the outside is cosine, and the derivative of the inside is the 2, okay? So we're going to set this derivative equal to 0. So the 2 is not going to matter. It's going to be the cosine of 2x that you want equal to 0. Okay, so we want where the cosine, where the x-intercepts are for the cosine, those occur at multiples of pi over 2 for the cosine. So if it's helpful, you can go ahead and draw the picture of the cosine so that you can see where I'm going to be getting these answers. So here's an x-intercept. Okay, here's an x-intercept, and then it'll repeat again at 5 pi over 2, etc. Okay, so we have pi over 2 is where the cosine has an x-intercept, 3 pi over 2, 5 pi over 2, and keep going if need be. Okay, now the good news is we're only looking at the interval between 0 and pi over 2. So let's see what happens when we divide by 2 here. So if we divide by 2, this 2 will join the 2 that we have. So we have pi over 4, 3 pi over 4, 5 pi over 4, etc. Okay, now we only want the value that occurs between 0 and pi over 2. So this one is outside of the interval, so definitely that one, and then any that follow. So the value that we're looking for in our interval where the derivative is 0 ends up being pi over 4. Okay, that completes part A for us. All right, for part B, our function is 1 minus the absolute value of x. We want to start off by checking the conditions. This would be a good one to draw the picture. So the absolute value of x is a V shape, okay? Normal absolute value of x, just FYI, looks like this, okay? All right, now our absolute value of x has been moved up 1 unit, and with the negative, it's been flipped down. Okay, so our graph ends up looking like the following. Okay, so it's moved up 1 unit. Okay, so we have this going on. Okay, but then it's been flipped down. Okay, so this is y equals 1 minus the absolute value of x. All right, so we can see that it's definitely going to be continuous everywhere. So it'll definitely be continuous on our interval, -1 to 1. Okay, so next we're checking that it's differentiable on our interval from -1 to 1, and we can see that we have a corner here, so we are going to have some problems at the x value of 0, okay, which is in our interval from -1 to 1. We're going to have a spot where the derivative does not exist because of that corner. Okay, so f is not differentiable on the open interval from -1 to 1 because of the corner at x equals 0 that we see from our graph. Okay, so therefore we're pretty much done at this point. We can't use or apply Rolle's theorem. Okay, and that completes part B of example 1.